Welcome to the unveiling of Cosmic Odyssey. Within the boundless expanse of the universe lies a ring of intrigue and wonder, the terrestrial planets. As we embark on this voyage of discovery, prepare to be captivated by the enigmatic worlds that orbit our radiant sun. From the fiery furnace of Mercury to the azure jewel of Earth, each planet holds a secret waiting to be unearthed.
Join us as we delve into the heart of this celestial deep stream, unraveling the mysteries and igniting the flames of curiosity.
Welcome, fellow travelers, to the dawn of a new era in planetary exploration. Now, let's explore the Earth. Earth is a terrestrial planet composed primarily of rocks and metals. The most abundant elements in Earth's crust are oxygen, 46.6%, and silicon, 27.7%, followed by aluminum, iron, calcium, sodium, potassium, and magnesium. The core of the planet is primarily composed of iron, 85%, and nickel, 5%, with smaller amount of sulfur and other elements. Earth has a diameter of about 7,970 miles, or 12,742 kilometers. Its equatorial circumference is about 24,901 miles, or 40,075 kilometers. Earth's mass is about 5.97 times 10 raised to 24 kilograms, making it the fifth largest planet in the solar system. Earth has an average density of about 5.52 grams per cubic centimeter. The density is higher in the core due to the presence of dense metal, while the outer layer have lower densities. Earth has a diverse range of surface conditions, including the continents, oceans, mountains, valleys, and various landforms. The planet has an average surface temperature of about 59 degrees Fahrenheit or 15 degrees Celsius. The highest recorded temperature on Earth was 134 degrees Fahrenheit or 56.7 degrees Celsius in Death Valley, California, USA in 1913. The lowest recorded temperature was negative 128.6 degrees Fahrenheit or negative 89.2 degrees Celsius at the Soviet Union's Vostok Station in Antarctica in 1983. Earth has an atmosphere primarily composed of nitrogen, about 78%, and oxygen, about 21%. The remaining 1% consists of trace amounts of carbon dioxide, water vapor, argon, and other gases. The atmosphere plays a crucial role in regulating temperatures, protecting life from harmful solar radiation, and enabling weather and climate systems. The atmosphere also contains the ozone layer, which helps shield the planet from harmful ultraviolet radiation.
Our understanding of the internal structure of Earth is based on a combination of seismic data, laboratory experiments, and theoretical models. Here is what is known about Earth's internal structure. The first one is the crust. The crust is the outermost layer of the Earth and is composed primarily of solid rocks. It varies in thickness, ranging from about 3 to 46 miles, or 5 to 75 kilometers beneath the continents, and about 3 to 6 miles, or 5 to 10 kilometers beneath the ocean basin. The crust is divided into two types: the continental crust, which is thicker and less dense, and the oceanic crust, which is thinner and denser. Next is the mantle. The mantle lies beneath the crust and extends about 1,000 miles or 2,900 kilometers deep. It is predominantly composed of solid rock, rich in silicate minerals such as olivine and pyroxene. The mantle can be further divided into the upper mantle and the lower mantle based on differences in physical properties and composition. Okay, so the third one is the core. The Earth's core is located beneath the mantle and is primarily composed of iron and nickel. It is divided into two distinct regions, the outer core and the inner core. The outer core, which is about 1,400 miles or 250 kilometers thick, is in a liquid state due to the high temperatures and pressures. The inner core, with a radius of about 760 miles or 1,220 kilometers, is solid due to even higher pressure despite the intense heat. Next is transition zones. There are several transition zones within Earth interior where there are significant changes in mineral phases and properties. One notable transition zone is the boundary between the upper mantle and the lower mantle, known as the Gothenburg discontinuity or the mantle transition zone. And the last one is the lithosphere and asthenosphere. The lithosphere is the rigid outermost layer of the Earth, consisting of the crust and a portion of the uppermost mantle. The asthenosphere is the partially molten and ductile region beneath the lithosphere, where there are solid rock and flow over long periods of time. It's important to note that our knowledge of Earth's internal structure is indirect, as we cannot directly observe or sample the deep interior. Seismic waves generated by earthquake provide valuable information about the structure and the composition of the Earth's interior. By studying how these waves propagate through the planet, scientists can infer the properties of the different layers. This understanding of Earth's internal structure is an ongoing area of research, and scientists continue and refine their models and theories based on new data and advancement in technology. The Earth's surface features and geographical characteristics are diverse and shaped by various geological processes. Here are some notable features. Number 1. Mountains. Earth has numerous mountain ranges such as the Himalayas, the Andes, the Rockies, the Alps, and the Appalachians. Mountains are formed through tectonic activity, including evolutions of tectonic plates, uplift, and folding of rocks. The second one is the valleys and canyons. Valleys and canyons are typically formed by erosion from water, wind, or ice over long periods. Examples include the Grand Canyon in the United States and the Nile River Valley in Egypt. The third one is the craters. Earth has impact craters, but they are relatively rare compared to the other celestial bodies due to the erosions and tectonic activity. Some notable impact craters include the Chicxulub crater in Mexico, which is associated with the extinctions of dinosaurs, and the Barringer craters in Arizona, USA. The fourth one is the volcanoes. Volcanoes are found in various regions across the globe, often occurring near tectonic plate boundaries. Volcanoes can be active, dormant, or extinct and formed by the eruption of molten rock or magma onto the Earth's surface. Examples include Mount Vesuvius in Italy, Mount Kilimanjaro in Tanzania, and Mauna Loa in Hawaii. The fifth one is the lava plains. Lava plains are large areas covered with solidified lava flows from volcanic eruptions. The largest lava plain on Earth is the Tigan Plateau in India, formed by extensive volcanic activity. The last one is the erosion and weathering. Erosion and weathering processes continuously shape the Earth's surface. Water, wind, and ice, and chemical reactions break down the rocks and transport sediments, contributing to the formation of valleys, canyons, and other features. Coastal erosions, caused by the action of waves, plays a significant role in shaping coastlines and creating features like waves and beaches. These surface features and geographical characteristics are dynamic and constantly evolving due to the geological processes, including the plate tectonics, erosions, weathering, and volcanic activity. Earth's diverse landscapes are a result of millions of years of geological activity and provide a rich and varied environment for life to thrive.
Earth's atmosphere is a mixture of gases that surrounds the planet and plays a vital role in supporting life and shaping weather patterns. Here are some aspects of Earth's atmospheric conditions. Number 1 is the composition of the atmosphere. Earth's atmosphere is primarily composed of nitrogen, about 78%, and oxygen, about 21%. Other trace gases, including carbon dioxide, methane, water vapor, ozone, and noble gases, make up the remaining fraction. These gases are crucial for maintaining a stable climate and supporting life as we know it. Number 2 is the greenhouse effect. The Earth's atmosphere exhibits a greenhouse effect which is essential for regulating the planet's temperature. Certain gases such as carbon dioxide, methane, and water vapor act as greenhouse gases. These gases trap heat from the sun, preventing it from escaping back into space and keeping the Earth's surface warmer than it would be otherwise. The greenhouse effect is necessary for maintaining a habitable temperature range on Earth but can be amplified by human-induced increases in greenhouse gas concentrations, leading to global warming and climate change. Number 3 is the weather patterns and atmospheric phenomena. Earth's atmosphere is dynamic and exhibits a wide range of weather patterns and atmospheric phenomena. Weather patterns are driven by the interaction of solar energy, the rotation of Earth, and the distribution of heat and moisture in the atmosphere. These patterns include the formation of high and low pressure systems, jet streams, fronts, and the circulation of air masses. Atmospheric phenomena such as clouds, precipitations, thunderstorms, hurricanes, tornadoes, and various types of atmospheric optics are also common. Number 4 is the atmospheric layers. Earth's atmosphere is divided into several layers based on temperature changes with increasing altitude. The lowest layer is the troposphere, where weather occurs and most of the Earth's mass is concentrated. Above the troposphere, there are stratosphere, mesosphere, thermosphere, and exosphere with distinct characteristics and compositions. Next is the ozone layer. The ozone layer is a region within the stratosphere that contains a higher concentration of ozone molecules. Ozone absorbs most of the sun's harmful ultraviolet ray or radiation, protecting life on Earth from its harmful effects. Human activities such as the release of chlorofluorocarbons have led to depletion of ozone in certain regions, particularly over Antarctica, which has environmental and health implications. Understanding and monitoring Earth's atmospheric conditions are crucial for predicting weather patterns, studying climate change, and assessing the impact of human activities on the environment. Understanding and monitoring Earth's atmospheric conditions are crucial for predicting weather patterns, studying climate change, and assessing the impact of human activities on the environment. Scientific research and observations help us improve our knowledge of atmospheric processes and their interactions with the Earth's surface and biosphere. Earlier, we discussed everything about the Earth. Now, let's move on to the Moon. The Moon is primarily composed of rock and metal. Its crust is made up of mostly oxygen, silicon, magnesium, iron, calcium, and aluminum. The Moon's interior consists of solid mantle and a small metallic core. The Moon has a diameter of about 3,474 kilometers, making it about 1/4 the size of the Earth. In terms of mass, the Moon is about 1.2% of Earth's mass. The Moon has an average density of about 3.34 grams per cubic centimeter, which is significantly lower than Earth's average density. The lower density suggests that the Moon has a higher proportion of lighter elements compared to Earth. The Moon's surface is covered in a layer of loose, powdery material called the regolith, which is made up of small rock fragments, dust, and impact debris. The Moon lacks an atmosphere, so it is exposed to the harsh condition of space, including temperature extremes, radiation, and micrometeoroid impacts. The Moon does not possess a significant atmosphere. It has an extremely thin exosphere which consists of scattered atoms and molecules, including helium, hydrogen, neon, and sodium. The exosphere is so tenuous that the particles rarely interact with each other and behave more like individual atoms than a traditional atmosphere. The Moon's surface is characterized by various features, including craters, impact basins, mountains, valleys, and lava plains. Impact craters are a prominent feature formed by the collision of meteoroids with the Moon's surface. The Moon also has large flat areas called maria, which are ancient lava plains formed by volcanic activity.
Understanding of the internal structure of the Moon is derived from various sources, including the seismic data, gravity measurement, and the analysis of lunar sample from the Apollo missions. Here is what is currently known about the internal structure of the Moon. The first one is the crust. The Moon crust is the outermost layer and varies in thickness across different regions. The first one is the crust. The Moon crust is the outermost layer and varies in thickness across different regions. The crust is composed mainly of igneous rocks such as basalt. The average thickness of the crust is about 50 kilometers or 31 miles on the near side, and 35 kilometers or 22 miles on the far side. Number 2 is the mantle. Beneath the crust lies the Moon's mantle, which extends to a depth of about 1,000 kilometers or 621 miles. The mantle is believed to be composed of densely liquid minerals, including the pyroxene and olivine. The third one is the core. The Moon has a small metallic core at its center, with an estimated radius of about 330 kilometers or 205 miles. The core is thought to be primarily composed of iron, with a smaller amount of sulfur and nickel. However, the exact size and composition of the core remain uncertain. The fourth one is the lunar seismic activity. The Apollo missions placed seismometers on the lunar surface, allowing scientists to study moon phase. The analysis of seismic data suggests that the Moon's interior is relatively seismically inactive compared to Earth. And the fifth one is the lunar heat flow. Measurement of heat flow from the Moon's interior indicate that it has a lower rate of heat production compared to the Earth. However, there are variations in heat flow across different regions of the Moon, suggesting localized thermal anomalies and potential remnants of past volcanic activity. And the last one is the lunar magnetic field. The Moon lacks a global magnetic field like Earth, but localized magnetic anomalies have been detected in certain regions. These anomalies are likely remnants of ancient magnetic activity when the Moon's core was still molten. It is important to note that our understanding of the Moon's internal structure is still evolving, and ongoing research and analysis of new data, such as data from lunar missions and future lunar explorations, will provide a further insight into the Moon interior. The Moon's surface exhibits a variety of features and geographical characteristics shaped by a combination of geological processes and the impacts over billions of years. Here are some prominent surface features of the Moon. The first one is the impact craters. The Moon is covered with numerous impact craters, which are circular depressions formed by a collisions of asteroids, meteoroids, and comets with the lunar surface. Craters come in various sizes, from small ones with a diameter of a few meters to large ones several kilometers wide. Here are some well-known impact basins include the Salt Aitken Basin and the Embryo, Trinitatis, and Grecian basins. Number 2 is the Maria. Dark, flat areas of the Moon's surface are called Maria, which means seas in Latin. These regions were once thought to be actual bodies of water, but are, in fact, ancient lava plains formed by volcanic activity. The Maria are primarily located on the near side of the Moon and are visible to the naked eye from Earth. Examples include the Sea of Tranquility and the Sea of Serenity. The third one is the highlands. The moon's highlands are brighter, like terrains that contrast with dark Maria. These areas are composed of heavily cratered, mountainous regions and are made up of anorthosite, a type of rock which in hydroclase feldspar. The highlands cover a significant portion of the moon's surface, especially on the far side. The fourth one is the rills. Rills are long, narrow depressions on the lunar surface. They can be categorized as either curved or straight. Some rills are believed to be collapsed lava tubes, while others may have formed due to the volcanic activity or tectonic forces. The fifth one is the mountains and ranges. The moons have several mountain ranges, including the Montes Apenninus, Montes Caucasus, and Montes Carpathus. These mountain ranges are remnants of ancient impact or volcanic activity. The tallest mountain on the moon, Mons Huygens, reaches a height about 5.5 kilometers or 3.4 miles. The sixth one is the volcanic features. The moon has evidence of past volcanic activity, including the volcanic domes and small shell volcanoes. These features indicate that volcanic eruptions occurred in the past, resulting in the release of lava into the lunar surface. And the last one is the erosion and weathering. Unlike Earth, the moon lacks significant erosions and weathering caused by the wind, water, or an atmosphere. However, micrometeoroid impacts and the effects of solar radiations over time can cause some degradation of breakdown surface materials. It is important to note that while moon surface has been extensively studied, our understanding of specific features continues to be refined as new data is collected in lunar missions and explorations.
The moon has an extremely thin and tenuous atmosphere, often referred to as an exosphere. Here are the key characteristics of the moon's atmosphere. 1. The composition. The moon's exosphere is primarily composed of scattered atoms and molecules, including helium, hydrogen, neon, argon, and other trace amounts of other gases. These gases are derived from various sources, such as the solar wind, outgassing of lunar surface, and cometary impacts. Second is negligible pressure. The atmospheric pressure of the moon is extremely low, almost negligible. The density of the exosphere is so low that it is considered a near vacuum. Consequently, the moon's atmosphere has no significant impact on human exploration or activities on its surface. Third is the greenhouse effect. Due to the thinness of the moon's atmosphere, there is no significant greenhouse effect. Greenhouse gases, which trap heat and contribute to warming, are not present in sufficient quantities to affect the lunar climate. Fourth is lack of weather patterns. Unlike Earth, the moon does not have weather patterns or atmospheric phenomena like clouds, precipitations, or wind. The absence of substantial atmosphere means that there is no mechanism for the formation of weather systems or transfer of heat and moisture. Fifth is the surface temperature extremes. The lack of an atmosphere and the moon result in significant temperatures variation. During the lunar day, the surface can reach extremely high temperatures exceeding 100 degrees Celsius or 212 degrees Fahrenheit. Conversely, during the lunar night, temperatures can drop to very low levels, as low as negative 173 degrees Celsius or negative 279 degrees Fahrenheit. It's worth noting that the moon's lack of substantial atmosphere is one of the factors that make it an inhospitable environment for life as we know it. However, the thin exosphere and the absence of atmospheric interference make it an excellent location for astronomical observations and the study of space phenomena. The moon has several unique and notable features and events that have captured the interest of scientists and astronomers. Here are a few examples.
Now, let's move on to the Mercury. Mercury is the smallest and innermost planet in our solar system, located closest to the Sun. Mercury has a rocky composition, primarily consisting of silicate minerals and metals. Its core is believed to be large and iron-rich, accounting for about 60% of the planet's mass. The outer shell, or mantle, is composed of silicate rock. Mercury has a diameter of approximately 4,879 kilometers or 3,032 miles, making it the smallest planet in our solar system. It has a mass of about 0.55 times that of Earth, making it one of the least massive planets. Due to its relatively large iron core, Mercury has a high average density of about 5.427 grams per cubic centimeter. This density is the second highest among the planets in our solar system after the Earth. Mercury's surface is heavily cratered, resembling the Moon's surface. It lacks the extensive volcanic plains found on other terrestrial planets like Earth or Mars. The surface exhibits a variety of features, including the impact craters, scarps or cliffs, and smooth plains. Mercury has an extremely thin and tenuous atmosphere, often referred to as an exosphere. The exosphere is composed of trace amount of gases, including helium, hydrogen, oxygen, sodium, potassium, and calcium. These gases are thought to originate from the solar wind, captured by Mercury's weak gravitational field. Mercury experiences extreme temperature variations due to its proximity to the Sun and lack of atmosphere to distribute heat. The surface temperature can reach up to 430 degrees Celsius on the Sun's lit side, while the temperature can drop for as low as negative 173 degrees Celsius on the Earth side. Mercury's unique characteristics, such as its small size, high density, heavily cratered surface, and extreme temperature conditions, make it a fascinating object for scientific study. Various space missions, including the NASA's Messenger and the European Space Agency, or BP Colombo, have provided valuable data and insight into the planet's composition, geology, and magnetic field.
From scientific studies and data gathered by space missions indicates that the planet has a layered composition with a relatively large iron core. Here's what is known about the internal structure of Mercury core. Mercury has a large, solid iron core that occupies about 42% of the planet's volume. The core is believed to have a radius of about 1,800 to 1,900 kilometers or 1,118 to 1,118 miles, accounting for about 60% of planet's mass. The core is surrounded by a thin layer of liquid iron, and it is thought to be responsible for generating a weak magnetic field. The second is the mantle. Surrounding the core is the mantle, a layer of silicate rock. The mantle is composed of minerals rich in iron and magnesium. It extends from the core mantle boundaries to the planet's surface. The thickness of the mantle is not precisely known, but it is estimated to be around 600 to 700 kilometers or 373 to 435 miles. The third is the crust. The outermost layer of Mercury is the crust, which is relatively thin compared to the other terrestrial planets. The crust is composed of various types of rocks, including basalt, a volcanic rock typically found in maria or dark plains on the surface. The crustal thickness is estimated to be around 35 to 40 kilometers or 22 to 25 miles. The presence of a large iron core and relatively small size of mantle and crust are distinctive characteristics of Mercury's internal structure. This composition is thought to have resulted from combination processes during its formation, including the accretion of materials during the planet's early stages and the subsequent differentiation of denser materials towards the core. Understanding the internal structure of Mercury provides valuable insights into its formation. Geophysical processes. Understanding the internal structure of Mercury provides valuable insights into its formation, geophysical processes, and the dynamics of its magnetic field. Space missions like NASA's MESSENGER or Mercury's surface space environment, geochemistry, and ranging have contributed significantly to our knowledge about Mercury's internal structure through measurements of its gravitational field, magnetic field, and surface composition. Mercury's surface features and geographical characteristics are diverse and include a range of formations, such as craters, mountains, valleys, volcanic plains, and scrubs. However, the planets lack significant erosion or withering processes due to its thin atmosphere and limited geological activities. Here are some of the prominent surface features of Mercury. First is the impact craters. Mercury's surface is heavily cratered, resembling the Moon's surface. It is covered with numerous impact craters of various sizes. These craters are formed by the impact of asteroids, meteoroids, and comets over billions of years. Some notable craters on Mercury include the Caloris Basin, which is one of the largest impact basins in the solar system, Rembrandt and Shakespeare craters. Second is scarps or cliffs. Mercury features long, steep cliffs called scarps, which are believed to be the result of the planet's construction as it cooled over time. These scarps extend for hundreds of kilometers and can be several kilometers high. The largest scarp on Mercury is the Enterprise Ropes, which stretches for more than 400 kilometers. The third is the smooth plains, or what we call Maria. Mercury has vast plains known as Maria, which are smooth, dark regions on its surface. These plains are believed to have formed from ancient volcanic activity where lava erupted on the surface and filled large impact basins. The largest and the most well-known of these plains is the Caloris Planitia. The fourth is volcanoes. Mercury shows evidence of past volcanic activity. However, compared to other terrestrial planets like Earth or Mars, the volcanic features on Mercury are relatively limited. The volcanic activity on Mercury is thought to have occurred earlier in its history, resulting in the formation of volcanic vents, lava flows, and small volcanic domes. The fifth is the mountains. Mercury has some mountainous regions. Although they are not as prominent as found on Earth or Mars, the highest mountains on Mercury is peaked within the Rachmaninoff Basin, reaching an altitude of about 4.48 kilometers or 2.78 miles above the surrounding plain. The last one is the valley and canyons. Mercury has a few large valleys and canyons, with the widest known canyon being the Great Valley. These features may have formed through a combination of tectonic activity, impact cratering, and the planet's construction. Due to the absence of significant geological processes like plate tectonics, erosions, and withering, Mercury's surface features have remained relatively well preserved over time. The exploration missions such as NASA's MESSENGER and the European Space Agency BP Colombo have provided valuable data and images that have helped scientists better understand the surface characteristics and geological history of Mercury. Mercury has an extremely thin and tenuous atmosphere, often referred to as an exosphere. The atmospheric conditions on Mercury differ significantly from those of Earth or other terrestrial planets. Here what is known about the atmospheric conditions of Mercury. First, the composition. Mercury's exosphere is composed primarily of atoms and ions that originate from the solar wind, a stream of charged particles emitted by the sun. The exosphere of Mercury contains trace amounts of gases, including helium, hydrogen, oxygen, sodium, potassium, and calcium. These gases are present in very low densities. The second is the greenhouse effect. Unlike Venus, which has a dense atmosphere causing a strong greenhouse effect, Mercury's thin atmosphere does not contribute significantly to a greenhouse effect. The lack of substantial atmosphere means that the heat from the sun is not effectively trapped, resulting in extreme temperature variations between the sunlit and the shadowed side of the planet. The third one is the weather patterns and atmospheric phenomena. Due to its thin and tenuous atmosphere, Mercury does not exhibit weather patterns or atmospheric phenomena like those found on Earth, such as clouds, storm, or winds. The atmospheric conditions on Mercury are relatively calm and static. The last one is the surface-bound exosphere. It's important to note that the exosphere of Mercury is closely tied to the planet's surface. The surface-bound exosphere is influenced by the interaction between the solar wind and the surface materials, resulting in processes like sputtering, atoms being knocked off on the surface, and vaporization of surface materials. Overall, the atmospheric conditions of Mercury are characterized by an extremely thin and tenuous exosphere composed of trace amounts of gases. The lack of substantial atmosphere means that the Mercury does not exhibit significant weather patterns or atmospheric phenomena like those found on Earth or Venus. The study of Mercury's exosphere provides valuable insights into the planet's interaction with the solar wind and the dynamics of its thin atmosphere. There are several unique and notable features and events on Mercury that distinguish it from other planets in the solar system. So here are a few examples. Now, let's move on to the planet Mars. Mars, often referred to as the red planet, has distinct characteristics that set it apart from other planets in the solar system. Here are the key characteristics of Mars. Mars is primarily composed of silicate rock similar to Earth and the other terrestrial planets. Its core is thought to be mostly made up of iron with smaller amounts of sulfur and nickel. Mars also has a polar ice caps composed of water ice and carbon dioxide ice. Mars has a diameter of approximately 6,779 kilometers, making it the second smallest planet in the solar system after Mercury. It is about 10.7% of Earth's mass, making it roughly half the size and mass of the Earth. Mars has a density of about 3.93 grams per cubic centimeter, which is lower than Earth's density. This suggests that Mars has a higher concentration of lighter elements and compounds in its composition, such as silicon and oxygen. Mars has a varied and diverse surface with features such as impact craters, volcanoes, valleys, mountains, and vast plains. The surface is predominantly red due to the presence of iron oxide in its soil and rocks. Mars also has the highest volcano in the solar system, Olympus Mons, and the deepest canyons, Valle Marineris. Mars has a thin atmosphere composed mainly of carbon dioxide with 95.3%, other gases include nitrogen with 2.7%, argon with 1.6%, and small amounts of oxygen, carbon monoxide, and water vapor. The atmospheric pressure on Mars is about 0.6% that Earth's surface pressure. The thin atmosphere contributes to the planet's cold temperature and lack of substantial greenhouse effect. The average surface temperature on Mars is around -63 degrees Celsius, but it can vary significantly depending on the location and season. Mars has a thin atmosphere that does not retain heat well, leading to large temperature fluctuation between day and night. Mars has a polar caps located at its north and south poles. These ice caps consist of water ice and carbon dioxide ice. Mars has a polar ice caps located at its north and south poles. These ice caps consist of water ice and carbon dioxide ice. During the Martian winter, part of the carbon dioxide in the atmosphere condenses and freezes, forming a seasonal layer of dry ice on the polar caps. Understanding the characteristics of Mars is crucial for studying its potential habitability, past climate, geological history, and the possibility of past or present life on the planet. Various missions, including NASA's Mars rovers and orbiters, have provided valuable data and images significantly advancing our knowledge of Mars and paving the way for future exploration.
Our current understanding of the internal structure of Mars is based on a combination of data from spacecraft missions, seismic studies, and theoretical models, while some details remain uncertain. Here is the general understanding of Mars' internal structure. Crust. In Mars, has a relatively thin crust compared to Earth, with an average thickness of around 50 kilometers or 31 miles. The crust is composed of basaltic rock, similar to the volcanic rocks found on Earth's shiny crust. Beneath the crust lies Mars' mantle, which extends a of about 1,500 kilometers or 932 miles. The mantle is made up of denser, more solid rocky material, including the silicates and iron-rich mineral rocks. Mars has a core that is thought to be partially molten. The core is composed primarily of iron, along with some nickel and sulfur. Its estimated radius is about 1,800 kilometers or 1,118 miles, accounting for nearly half of the planet's radius. The exact size and states of Mars' core are still uncertain, and there are two main hypotheses. The solid inner core. Some models suggest that Mars has a solid inner core surrounded by a liquid outer core. The solid inner core may have formed due to cooling and solidification of iron-nickel alloy over time. And the second one is partially molten core. Other models propose that Mars' core is partially molten, with a solid innermost region and a liquid outer region. This idea is supported by studies of the planet's magnetic field, which suggests the presence of a dynamo generated by the motion of liquid metal in the core. It is important to note that our understanding of Mars' internal structure is still evolving, and future missions, such as NASA InSight mission, will provide more detailed data and insight into the planet's interior through seismic measurements. By studying Mars' internal structure, scientists aim to better understand its geological history, the processes that shape its potential for habitability. Mars exhibits a variety of surface features and geographical characteristics that have been observed through spacecraft missions and telescopic observations. Here are some prominent features on the Martian surface. Impact craters. The Mars, like the Moon and other rocky bodies, is covered with impact craters. These craters are formed by the impact of asteroids, meteoroids, and comets. Some notable Martian impact craters include the Hellas Planitia, Argyre Planitia, and the large and ancient impact basin known as Borealis Basin. Volcano in the solar system, Olympus Mons. This shield volcano stands about 22 kilometers high and has a diameter of over 600 kilometers. Mars also has other prominent volcanoes such as Ascarius Mons, Babinos Mons, and Arsia Mons. These volcanoes are characterized by broad, gently sloping flanks. In terms of valleys and canyons, Mars features several impressive valleys and canyons. Most notable is Valles Marineris, a system of interconnected canyons that stretches for over 4,000 kilometers in length, making it the longest known canyon in the solar system. Valles Marineris reaches a depth of about 7 kilometers and is believed to have formed through a combination of tectonic and erosional processes. Other notable Martian canyons include the Mars Valleys and Niger Valleys. In plains and plateaus, Mars has vast plains and plateaus that cover large portions of its surface. The northern plains have relatively smooth and flat, while the southern hemisphere is characterized by more branched and cratered highlands, such as the Terrestrial and Elysium volcanic regions. Mars include Acidilia planitia, Amazonas planitia, and Utopia planitia. Mars has a polar ice caps at its north and south poles. These ice caps contain a combination of water and carbon dioxide, ice, or dry ice. During the Martian winter, part of the carbon dioxide in the atmosphere condenses and freezes, forming a seasonal layer of dry ice in the polar caps. Lastly, erosion and weathering. While Mars is a dry and arid planet today, evidence suggests that it has experienced a significant erosion and weathering in the past. Channels and river-like features such as Aris valleys and Ma'alim valleys indicate the presence of flowing water in Mars' ancient history. Wind erosion has also shaped the Martian surface, creating a dune fields and winds called rock formation known as yardams. Studying the surface features and geographical characteristics of Mars provides valuable insights into a geological history, climate, and potential for past or present habitability. Ongoing and future missions such as the Mars rovers and orbiters will continue to explore and reveal more about fascinating landscapes of the red planet.
The atmosphere of Mars is distinct and significantly different from the Earth. Here are some key atmospheric conditions on Mars. First, the composition. Mars has a thin atmosphere composed primarily of carbon dioxide, about 95.3%. Other gases present in smaller amount include nitrogen, which is 2.7%, argon, 1.6%, and trace amounts of oxygen, carbon monoxide, and water vapor. Unlike Earth, Mars has a negligible amount of free oxygen in its atmosphere. Second, the greenhouse effect. While Mars has a substantial amount of carbon dioxide in its atmosphere, its greenhouse effect is relatively weak compared to the Earth. The thin atmosphere and low concentration of greenhouse gases contribute to Mars' colder temperature and less efficient heat retention. The third is the atmospheric pressure. The average surface pressure on Mars is about 0.6% that of Earth's surface pressures. Pressure is roughly equivalent to the atmospheric pressures at altitude of 35 kilometers or 22 miles above the Earth's surface. The low atmospheric pressure on Mars has implications for boiling and freezing points of liquid, and one is the weather patterns. Mars experiences weather patterns similar to Earth, including dust storms, clouds, and seasonal changes. Dust storms on Mars can be massive and cover large areas, sometimes enveloping the entire planet. These storms can last for weeks or even months, affecting atmospheric conditions and surface visibility. The fifth is the seasonal variations. Mars has distinct seasons due to its tilted axis and elliptical orbit. The changing seasons on Mars cause significant variations in temperature, atmospheric pressures, and the behavior of surface features such as polar ice caps. During the Martian winter, carbon dioxide freezes out of the atmosphere, causing the polar ice caps to expand. The last one is the atmospheric phenomena. Mars exhibits atmospheric phenomena such as clouds, fog, haze, Clouds on Mars are typically composed of water ice crystals or carbon dioxide ice crystals. Thin hazes can also be observed in Martian atmosphere, often due to the dust or the other particulate matter suspended in the air. Understanding the atmospheric conditions of Mars is crucial for studying its climate, weather patterns, and potential habitability. Spacecraft missions such as the Mars rovers and orbiters have provided valuable data on the Martian atmosphere, and ongoing research continues to deepen our understanding on this intriguing planetary environment. Mars, often referred to as the Red Planet, offers several unique and notable features and events that have piqued scientific interest. Here are some of the most noteworthy aspects of Mars. We're down to the last planet to explore. That is Venus. Venus, often referred to as Earth's sister planet, has distinct characteristics that set it apart from the other planets in our solar system. Here are the key characteristics of Venus. Is the composition. Venus is primarily composed of rock and metal. Its rocky mantle is mostly made up of silicate minerals, while its metallic core consists of iron and nickel. Second is size and mass. Venus is similar in size to Earth, with a diameter of about 12,104 kilometers or 7,521 miles and a mass of about 4.87 times 10 raised to 24 kilograms or 0.815 times the largest planet in the solar system. The third one is density. Venus has a density of about 5.24 grams per cubic centimeter, which is similar to Earth's density. This suggests that Venus has a composition similar to Earth, with a dense metallic core and a rocky mantle. Fourth is the surface conditions. Venus has a hostile and inhospitable surface environment. It is characterized by extreme temperatures, high atmospheric pressures, and a thick atmosphere composed mainly of carbon dioxide of about 96.5%. The surface temperature of Venus can reach up to 470 degrees Celsius or 878 degrees Fahrenheit, making it the hottest planet in our solar system. Venus also experiences a runaway greenhouse effect, trapping heat and keeping the surface temperatures elevated. The fifth is the atmosphere. Venus has a dense atmosphere composed mainly of carbon dioxide, which traces nitrogen and other gases. The atmospheric pressure at the surface is about 92 times that of Earth's surface pressure. The thick atmosphere creates a strong greenhouse effect, causing a significant temperature increase. The atmosphere also contains clouds composed of sulfuric acid, which is create a reflective layer that contributes to the Venus' high albedo. The last one is the surface features. Venus has a relatively young surface, with extensive volcanic activity even in its geological features. It has numerous volcanoes, including large-scale volcanoes and smaller volcanic features such as lava domes. Venus also has extension plain called planetary and a few highland ridges. However, the planet's surface is mostly obscured by thick clouds, making direct observation challenging. Understanding the characteristics of Venus provides insight into the processes that shapes terrestrial planets and the effect of extreme greenhouse conditions. Despite its inhospitable surface, Venus remains an intriguing target for scientific study, and future missions aim to further explore and unravel the mysteries of neighboring planets. Now, let's move on to the internal structure of Venus. First is the core. It is believed that Venus has a solid, metallic core at its center. The size and composition of the core are not precisely known, but it is thought to have a radius of about 3,000 to 3,500 kilometers. The core is primarily composed of iron and nickel, similar to the cores of other terrestrial planets. Next is mantle. Surrounding the core is the mantle, which is predominantly composed of silicate minerals. The mantle extends from the core to the surface and responsible for most of Venus' internal heat. The exact composition and properties of the mantle are still uncertain, but it is likely consists of silicate rocks, including various minerals such as pyroxenes and olivines. Next is the crust. The outermost layer of Venus is the crust, which is composed of solid rocks, primarily basaltic and granitic rocks. The thickness of the crust is estimated to be around 30 to 50 kilometers, although variations in different regions are possible. Next is the lithosphere. The lithosphere includes both the crust and the uppermost rigid part of the mantle. It is divided into tectonic plates similar to Earth's lithosphere, although the dynamics of Venus' tectonic activity are not yet fully understood. Next is lack of plate tectonics. Unlike Earth, Venus does not appear to have active plate tectonics, where the lithospheric plates move and interact with each other. This lack of plate tectonics contributes to the absence of significant recycling of Venus' crust and may have implications for the planet's geological evolution. While our understanding of Venus' internal structure is improving, there is still much to learn. Future missions and advancement in observational techniques will help refine our knowledge of planet's internal composition, dynamics, and geological processes. Venus has a diverse range of surface features and geographical characteristics, including craters, mountains, valleys, canyons, volcanoes, lava plains, erosions, and weathering. Here are some of the notable features. Number 1 is the craters. Venus has impact craters caused by the collision of meteoroids with its surface. However, the number of craters is relatively low compared to the Moon or Mercury. This is due to Venus' thick atmosphere, which causes most small meteoroids to burn up before reaching the surface. The craters on Venus tend to be relatively large, with diameter ranging from few kilometers to over 200 kilometers. Next is the volcanoes. Venus has a significant number of volcanoes, including both shield volcanoes and smaller volcanic features. The shield volcanoes on Venus are some of the largest in the solar system. The most famous volcano on Venus is Olympus Mons, which is much larger than its counterpart on Mars. Venus also has other volcanic features such as lava domes and small volcanic cones. Next is the lava plains. Venus has vast lava plains known as planetae, which cover a significant portion of its surface. These plains are made up of extensive volcanic flows that have erupted and spread across the surface. Some of the lava plains in Venus are enormous, covering areas comparable of the continent of Earth. Number 4 is mountains and ridges. Venus has various mountain ranges and ridges, including the Maxwell Montes, which are the highest mountains on the planet. These mountain ranges are primarily composed of folded and folded terrains, resulting from tectonic activity and crustal deformation. Number 5 is the valleys and canyons. Venus has numerous valleys and canyons that have been shaped by geological processes. The most prominent example is the vast feature called Aphrodite Terra, which contains of highland plateaus, rift valleys, and canyons. The canyons on Venus can be hundreds of kilometers long and several kilometers deep. And lastly, the erosion and weathering. Venus experiences some degree of erosion and weathering, although the exact processes are not well understood. The planet's thick atmosphere likely contributes to wind erosion, and there may be some chemical weathering occurring on the surface due to the presence of sulfuric acid in the atmosphere. It's worth noting that the surface of Venus is challenging to observe directly due to its thick atmosphere, which obscures much of planet's surface features. However, the data collected by spacecraft missions like NASA's Magellan have provided valuable insights into the geological characteristics and surface features of Venus.
Venus has a dense and inhospitable atmosphere with unique atmospheric conditions. Here are the key characteristics of the Venusian atmosphere. The atmosphere of Venus is primarily composed of carbon dioxide, which makes up about 96.5% of atmosphere. Nitrogen is the second most abundant gas, accounting for around 3.5%. There are also trace amounts of other gases, including the sulfur dioxide, water vapor, and various sulfuric compounds. In terms of greenhouse effect, the Venus exhibits an extreme greenhouse effect, which contributes to its high surface temperature. The thick atmosphere traps heat radiating from the surface, leading to a runaway greenhouse effect. The greenhouse effect on Venus causes surface temperatures to soar around 470 degrees Celsius, making it the hottest planet in our solar system. In atmospheric pressure, the pressure of the surface of Venus is about 92 times greater than Earth's surface pressure, equivalent to the pressure experienced at a depth around 1 kilometer or 0.6 miles in Earth's oceans. This high atmospheric pressure is a result of a massive amount of gas present in the Venus atmosphere. In terms of weather patterns, the Venus experiences a variety of weather patterns, including the high-speed wind and atmospheric circulation. Venusian winds can reach a speed up to 300 kilometers per hour or 186 miles per hour at the cloud tops. The atmosphere also exhibits a phenomenon known as superrotation, where the winds and upper cloud levels circulate much faster than the planet's rotation. Completing a full rotation is about 4 Earth days. In clouds, Venus' atmosphere is shrouded in thick clouds composed of mainly sulfuric acid. These clouds are located at altitude of about 50 to 70 kilometers or 31 to 43 miles above the surface. The clouds reflecting a significant portion of sunlight back into space. And the last one is the atmospheric phenomena. The Venus experienced various atmospheric phenomena, including the lightning and thunderstorm. Lightning discharges have been detected in Venusian atmosphere, and the thunder-like sounds known as whistles have been observed by spacecraft. Venus also exhibits a phenomenon called Venusian halos, which are bright rings and light sometimes observed around the sun or moon due to the lightning scattering by sulfuric acid clouds. The extreme condition of Venus' atmosphere make it a challenging environment to explore. However, spacecraft missions like NASA's Venus missions and future missions aim to study and unravel the mysteries of Venus' atmosphere, its dynamics, and its impact on the planet's surface conditions. Venus has several unique and notable features and events that set it apart from other planets. Here's some of them. And that's all for our presentation about the terrestrial planets and the moon.
Did you learn anything? Well, that's good. But before we end this presentation, we would like to leave this message. Just like the terrestrial planets, our journey of learning is marked by rocky terrain and challenges. But it's in overcoming these obstacles that we discover our true strength and resilience. Again, I am Crystal Joy V. Di Matawaran.
I am Jillian Marie V. Cerelius.
And I am models and device, and thank you for listening. Wait, wait, wait! Everybody say terrestrial planets! Louder! Terrestrial planets!